Okay, so I think it's time for us to begin the fourth lecture on first order predicate logic and model theory. So it's my pleasure to welcome Athipat once again to give us a lecture. So Athipat, go ahead. You're muted, and you should be able to share a screen now.
Right.
Yeah.
Yeah. Okay. Okay. So I just realized that I shouldn't put the date in here because for some attendants, right, you are not in the same time zone as I am. So this might be very confusing. But yeah, okay, I have it on anyway. It's just like a reminder for me. Okay. So let's look at the next part. For today, we're going to talk about types. Last time we already talked about definable sets, right? Definable sets. So we have last time we have a structure and we have a language. This is a structure. This is our language out. And you know that when we have a definable set, it is a set that is of the form. It is set of A that is in M to the N, such that M satisfy phi of A. Right? Okay, so we can describe set using formulas from our language. And that's usually what we do when we're trying to give a definition of a set. And today we're going to look at something from a different point of view. So let's just think about it this way. So here, let's think that we have an object A. Okay. We have an object A, or you can think of A as a person. Okay. Usually when you have a friend and you want to describe this person to one of your friends, let's say that this person A is not here right now. So what you usually do is we will try to describe how he looks, what is he doing, how old is he, or something like that. You can think of it as we trying to give a description of him, right? So here you have one description, the second description, and so on. Trying to list all the properties that he satisfied, these persons satisfied, and trying to let this describe him. Right? So by looking at it this way, you can see that when you have an object A, you can try to think about what are the possible properties that this person A have, right? And in this case, we're going to call this the type of A or something. Okay. You say the mic is changed. Let me adjust my mic position a little bit. Let me check. Is it better?
Yeah, I think it sounds better now. Thanks.
Okay. Okay, now let's look at the definition of the word type. And N type. Okay, so let M be a structure, and we have A be a subset of M, and N type over A is a set sigma X of LA formula. So we allow to use these parameters A in our formulas here with free variables among x up to x equal to x1 up to xn. Okay, so when you have n types, it means you describing n tuples. Okay, and we say that an n type is consistent if it is consistent with your structure M. Right? If it is consistent if the theory of M with the parameter from the set A union with the sigma x is consistent. Okay, so you add new sigma x into here and it is consistent. And usually when we talk about consistency, we talk about set of sentences. In here, you can consider x here as fresh constant. You treat these variables as fresh constants. So now you can think of it as something in your as sentence now. And we say that your n type is complete if for every LA formula phi x, either phi is in sigma x or not phi is in sigma x. Okay. And here I have a notation for the set of all complete consistent n types over A. I have SNMA, this guy, denote the set of all complete and consistent n type over A. And if M is clear from the context, we're gonna use just SNA for short. Okay, so now you may, can we have an examples of a complete consistent n type? The easiest way to construct to see an example of a complete consistent n type is, let's say you have a structure M and you have an object B that is an n tuples in M. We can look at what we call the type of B over A, which is the set of all formula phi x that is an LA formula that M satisfy phi B. Okay, so we look at the object B that we have, and we're trying to list all the possible properties of B and put it in this set. Okay, so it's just like we're trying to describe B as complete as possible. So look at all possible formulas and add it in here. Okay, now we also have that, and that's from the syntactic point of view. We can look at the type from semantic side. Here, let's say sigma x is an n type. We say that sigma x is realized in M if sigma x is a subset of the type of B over A for some B in Mn. Or you can just say that there is an object B such that M satisfies phi B for every phi that is in sigma x. Okay, and we're gonna say that it is finitely realized in M if every finite subset is realized in M. Okay, so now let's look at this example. Here we have M is the structures on with less than or equal to on the integer z. And here I can let A be equal to the set of natural number. Okay, here you can look at sigma 1x. Okay, which is the set of all x that is less than or equal to n for every n that is in the natural number. You can look at sigma 2x, which is the set of n less than or equal to x, where n is a natural number. And you can look at something like this, sigma 3x, when n is less than or equal to x. So sigma 3x is a union of these two sets, n less than or equal to x when n is a natural number and n less than or equal to 2, and x is less than or equal to m is in natural number, and m is greater than or equal to 3. Okay, so now you can look at this one. Let's do it one by one. So when you look at this sigma 1, right? When you consider sigma 1, you can see that you're working in these integers with less than or equal to, which means that you can consider any integers in here. And you can see that when you consider -1 is less than or equal to n for every n that is a natural number. So in this case, you can say that sigma 1 is realized in M, because you can see that -1 is the witness of this sigma 1 here. Now, when you consider sigma 2, sigma 2 is interesting. Here you can see that if there is something that is satisfied sigma 2, it must be greater than or equal to n for every n that is in a natural number, right? If there is something that is that satisfies this guy, it must be greater than n for every n that is in here. So in this case, you know that the integers doesn't have that contain any object with that properties. Well, you're gonna have that this guy is not realized in M. Is not realized in M. However, if you take any finite subset of sigma 2, right? If you take any finite subset of sigma 2, you can see that you can take the maximum of all the n's that occur in there, and that's going to be the witness for those finite subset. So you can see that even though sigma 2 is not realized, but it is finally realized. Okay, so that's those are examples. And for sigma 3, okay, so here for sigma 3, you can see that this is not realized. It means that if there is an x that satisfies sigma 3, it must be something that is greater than or equal to 2, right? But less than or equal to 3. So this is not realized in M and not finally realized as well. Okay, now that's something that you can that you get from those examples. Okay, so or you can look at something else. You can have the structures of the real field, real order field, and you can look at this set A, which is the set of the rational numbers. Here you can see that for each r that is a real number, you can let sigma r to be the set of a less than x and x less than b. When a and b are rational numbers, such that a is less than r and r is less than b. Okay, so that's something that you can have. And you can have something like sigma infinity. Sigma infinity is the set of all A that is in Q, set of A that is less than X, formulas A less than X, less than, a little bit, I need to be clarified here. When I write A less than B, it means A is less than or equal to X, and A is not equal to X. Okay. Okay, and now that we have the sigma infinity, we also have sigma minus infinity, which is the set of X less than B for every B that is in the rational numbers. Okay, now you can see that when you look at sigma R, you can see that R gonna realize this sigma R for any real number R is gonna realize sigma R. And when you consider sigma infinity and sigma minus infinity, you can easily see that this is not realized. In our structure M, but it is finally realized, right? Yes. Sorry, let me check it real quick. Right, it is finally realized. Okay, so those are something that we can consider. Okay, now actually, when you think about types, this is the semantics point of view of the types, right? And we also have the syntactic point of view of type. Actually, these two have some connection. Okay, and in order to see that, let me introduce a proposition here. So let M and M be structures such that M is elementary equivalent to N. Then there exists structures N prime that you can embed both M and N into those structures, right? So the picture is here. So you have M that is elementary equivalent to N. Then you can have a new structures N prime that you can embed these two into that structure. Okay, so how can we prove it? So first, I'm gonna assume that M is elementary equivalent to N. And with a loss of generality, we may assume that M and N are disjoint. Okay. If it's not disjoint, you can try to make it disjoint by changing the domain, right? You can look at the isomorph. You can look at an isomorphic version of these M and these N by adding, looking at instead of M and N, you can think of it as tuples and trying to distinguish them using the first coordinate. Okay, now that you have these M and N are disjoint, right? And you want to show that there exists an elementary embedding from G to from M to N prime and N to N prime. So what we can do here is we will show that the theory of M union the theory of NN is consistent, right? So if you have this theory, right, and you have a model of this one, you know that there must be an elementary embedding from M, from the first guy. Since it that satisfies this guy, you can have elementary embedding from M to those structures. And for this guy, if you have gonna have an elementary embedding from N to that guy. Okay, let me point out a little bit. This is consistent as L, M union N theory. Okay, so here we add constants to these structures, to this theory. Okay, I think there was a question, but can the set of ties be related by a partial order? So that a type A is also a type B. Oh, okay. I think let me finish this proposition and I'll come back to that question then. Okay. Okay, so here we will show that M union is consistent, right? Okay, so in order to prove this, we will suppose that it is not true. Suppose not. Then you're gonna have by compactness theorem, there must be some there must be like finitely many of them that is not inconsistent, right? So in those case, you also have that you're gonna have sigma 1 from THMM, and you're gonna have sigma 2 from the axis. Their axis, sigma 1 from THMM, and sigma 2 from THNN, such that the set of sigma 1, sigma 2 is inconsistent. Okay, so here you have sigma 1 and sigma 2 is inconsistent. Okay, but when you look deeper into these two sentences, you can see that sigma 1 gonna use constant from M only, and sigma 2 gonna use constant from N only. So here we can let theta 1 x1 up to xn, and theta 2 y1 up to ym be our formula such that you have that sigma 1 is equal to theta 1, and then you have a1 up to an, and sigma 2 is equal to theta 2, b1 up to bm, where a1 up to an is in M, and b1 up to bm are in N, are distinct. So you have a collection of all distinct parameters that occur in sigma 1 and sigma 2, and you can list all of them, and you know that they are disjoint, so you can use separate symbols to represent it. Here, since we know that sigma 1 and sigma 2 is inconsistent, right? Then you also know that there exists x1 up to there exists xn, phi x1 up to xn here, and there exists y1 up to there exists yn here. Phi, it's not phi, it's theta. Theta 1, theta 2, y1 up to yn is also inconsistent. Okay. So now you're going to have that. Hence, you're going to have that when you consider that exists x1 up to there exists xn, theta 1 x1 up to xn, right? This guy must be in THM, the theory of M, because M satisfies this guy. Hence, since you know that M is elementary equivalent to N, you're gonna have that there exists x1 up to xn is in theta 1 x1 up to xn as well. Okay, so that means the theory of M theory of N satisfy this guy. N satisfy this guy. But since you know that there exists y1 up to there exists yn, m, there are two y1 up to ym is also in here. You get that DHM is inconsistent, it is absurd, which is absurd. Okay, so that's how we show that we can construct this extension. Okay, now let me go back to Michael's question. Can the set of type be related by a partial order so that type A, type over A is also a type over B? Okay, so here you mean, let's say, for example, if you have A, which is a subset of B, right? You can have that if you have a type, if sigma, if you have A is a subset of B, if sigma is a type, an N type over A, then you can get that sigma is an N type over B. Okay, so if you have if you have A, which is a set of parameters, if you enlarge the set of parameters, then it's still a B type. Okay, so that's something that you can get. But things are going to be a little different if you're talking about the complete consistent N type, right? You can embed it into a complete consistent N type, but it's not complete in the new set of parameters. Okay, and what else do we know about types? We can have some connection between the consistency of type and the fact that it is finally realized. Okay, here you gonna have that if you have sigma x is an N type, the following are equivalent. You have that sigma x is finally realized if and only if sigma x is consistent, and if and only if it is realized in some elementary extension of your structure M, and it's also consistent in here. Okay, so let me give them the number 1, 2, 3, and 4. You will have that 1 implies 2 follows immediately from compactness theorem, right? Because it is finitely realized. To show that it is consistent, you need to show that it is satisfiable, right? To show that it is satisfiable, what you need to do is you just need to show that it is finally satisfiable, and that's just condition 1, say. And for the next part, for 2 implies 3, that where we need the previous proposition. Here, assume that sigma x is consistent, right? Which is mean that you have THMA union sigma x is consistent. Okay, so what do we need here? And we want to show that this is finally realized, right? Okay, so in order to show that this is finally realized, so what we need to do is we need to find some structures that that satisfy this guy. Okay, so here you need a structures and elementary extension that satisfy this guy. So what we can do here is we can consider THMM and union sigma x. Okay, here you want to construct a structure that satisfies this guy. You want a structure that satisfies this guy. Oh, okay. So let's, I got confused a little bit. Okay, so let's say that this is consistent, right? So what does this consistency mean? So it's mean that you have that then THMA union sigma x is consistent. Right. So what does this one mean? It's mean that there exists and structures and LA structure N such that N is a model of THMA, right? Union sigma x. Okay, so it's mean that it is a model of this guy, and there exists B in N such that B realizes sigma x. It satisfy every sense formulas in here, right? Okay, now what else do we know about this? Here, since N is a model of THMA, then you're gonna get that N is elementary equivalent to MA as an LA structure. Okay, what else do we have here? Since it is an L structure, then you can construct n prime by previous proposition. You can have n prime that is an LA structure. There is n prime and LA structure such that you can assume that this MA is an elementary substructures of n prime, and there is an elementary embedding G from n to n prime. Okay, so now when you look at this, since this G is an elementary embedding, you can get that G of B gonna realize sigma X. Okay, so here you're gonna get that G of B is gonna realize sigma X in this n prime. Okay, so now you have an elementary and extension M of MA, and that is called n prime, and this guy is realized in n prime. GB sigma X is realized in n prime. So, but what we want to get is we want to get an elementary extension of M. So to finish this, we take the reduct, take N, take the reduct of N prime to L. And that's going to complete this part. Okay, so now we know that right now we have that it is finally realized. Realize implies consistent, implies realize in elementary extension. Okay, so that's what we have right now, and we can show that if it is realized in elementary extension, you're gonna have that it is this guy is also consistent, and that's just immediately from 3 implied 4 is trivial. It's trivial. And then for 4 implied 1, so we want to show that this is finally realized, right? So suppose THMM, this is also trivial. Sigma X is consistent, right? So if it's consistent, then it is finally consistent. And if it is finally consistent, then it is finally realized. Then, so here you get that sigma X is, okay, so let me point it out. So since this guy is realized, so this is consistent. So here we let's delta be a finite subset of sigma X. Be finite. Right. Okay, so what do we have here? Since this is a finite subset of here, then you get that THMM, right? Union delta X is consistent as well. What so let me see what I so let's see. Let's P is realized in some suppose it is in here. Oh, then sigma X is realized in some elementary extension M prime of M. Right. So if it is realized in some elementary extension of M, right. Okay, so here you get that it is finally realized in some elementary extension of M. And here we can let delta X be a subset of sigma X be finite. Then you're gonna have an object B. There exists B that is in M prime such that B satisfy B realizes delta X. But you can consider this delta X and see that it is consists of formula, only finitely many formulas. Let me use K here. Okay, so it's realized the sky. So which mean that you have hence M prime gonna satisfy directrix X and phi1 X I from 1 to K phi Ix. So when M prime satisfy this, then since M is an element, M prime is an elementary extension of M, so you get M satisfy directrix X and I equal to 1 to K of phi Ix. Okay, so that's how we get it. Sorry about that. Okay, so now you can see the connection between the consistency finally realized and it is realized in some elementary extension. Okay, so these also give another it also implies something. If you have a T that is a complete consistent theory, and if you have M and N are model of T, then you're gonna get that if you look at the set of all N type over M and N type in M and N type in A in N, then you're gonna get that these two types they are the same, right? You can see that when you look at the set of complete consistent N type, every object in here is a set, is a type, right? Is an N type, which is a set of L and L formulas. Right. So you can see that in the object that is in here is not related to this n or n. Right? So you can say that these two things are equal. So when you consider it as set. Okay, and you can also look at example of something like this. Here you have K be an algebraically closed field of characteristic P, where P is either 0 or prime. Right, and you have a F and F that is a subfield of K. You can consider for P that is in a complete consistent type P. You can consider something like this. You can consider this IP, which is the set of all polynomials over F, such that Fx is not equal to 0. And when you consider here, this is a when you consider F as a polynomial, you have it here. And when you consider F each polynomials with coefficient from F, you can consider it as an LF term, right? Which means that if this is an LF term, this is an atomic formula in LF. Okay, now you can consider this. So you can see that when we have something like this, when you have P that is in S and F, right? You're gonna get that this IP is a prime ideal. Okay, so here if you have P be a complete consistent in type, you can show that when you consider this I sub P, this I sub P gonna be a prime ideal in F of X. Okay, and when you know that this is a prime ideal, then you can know that it is finally generated. In here. Okay, and it is quite nice because by looking at something like this, you can count the number of S and F, right? By instead of counting this guy directly, which is kind of hard, if you know that if F is countable, then you're gonna get that the cardinality of this is gonna be countable as well. So you get only less than or equal to in from this argument. Okay, so here you have S and F is less than or equal to a Lebesgue, or it is countable, for example. Okay. Now you can also consider when you look at this SNF, SN of A, you can also equip it with a topology on the to here. So here we can look at what we call the stone topology on SNA. Stone topology on SNA is the topology that is generated by these bases of open set that is given by user phi is the set of P that is in SNA, where phi is in P. For every LA formula phi x. So we're gonna take a formulas and look at all the possible type that contain those formulas. Okay, and it's turned out that when we equipped SNA with this topology, you're gonna get that this SNA is compact, Hausdorff, and totally disconnected. The totally disconnected mean the only connected set is the singleton. Okay, so now you can see that this part is not hard, because when you look at the complement of any basis here, you're gonna get that when you look at all the types that does not contain P, since you're working in a structures M, right? If it doesn't contain P, it mean negation of it must it must contain the negation. So you're gonna get that this guy is equal to this guy. What does this one mean? It means that the complement of every U phi is open, right? Which means U sub phi is a clopin set, which is a set that is both open and closed. Okay, and by having this, we immediately get that it is both Hausdorff and totally disconnected. And to see that SNA is compact, so what we can do is we can start by giving a basis for SNA. No, a cover. We can give and we can. It is enough to consider a cover that is generated by these bases. The cover of SNA. Okay, so here you can consider this cover of SNA. Okay, so now what does this one mean? Oh, sorry about that. Let lambda be a set of LA formula and can see be a cover of SNA. Okay, so let's see how we can get it. Okay, so we want to say that this guy is a cover of SNA, right? So what can we do here in order to get that? This is a cover of what can we do to say that this has a finite subcover? So let's suppose not. Suppose C has no finite subcovered. Okay, so if this guy has no finite subcovered, it means that if you look at any finite subset of C, you should be able to find a type P that is not in the union of those guys, right? Okay, so now you can look at this. Then what does this one mean? Then for every finite subset delta of lambda, there is an n type P such that P is not in the union of U phi, where phi is in delta. Okay. So, and that will mean not phi is in P for every phi that is in delta, in delta. Okay, so what can we do here? So what can we do here is, in that case, here you can see that from this, it kind of hints us that we can consider something like this. So let sigma to be the set of not phi for every phi that is in these lambda. Okay, so here you can consider sigma, which is not phi, and phi this for every phi that is in lambda. Okay, now you can show that from those properties, then you're gonna get that then sigma is consistent. So here you can get that sigma is consistent, and you can use Son's lemma. By using Son's lemma, you can extend this sigma to a complete, let P be P prime, let Q be a complete, consistent, n-type containing sigma. Okay, and now you can show that hence Q must not be in the union of phi lambda for U phi in here. So we, by doing something like this, we obtain an object that is not in the cover. So this is absurd. Okay, so that's how we show that this is compact. Okay, so that is a very nice interpretation of how we can look at the space of complete, consistent n-type. We can equip it with topology on it, and we also know some topological properties of it. You know, that is compact and Hausdorff and totally disconnected. Okay, so those are those are some something that we can consider when we have types. And next, when we consider type, we usually like to use these type to classified type of structures and theory. Okay, so next part, we're going to look at what we call kappa saturation. Let kappa be an infinite cardinal. We say that structure M is kappa saturated if for every A that is a subset of M, if the cardinality of A is less than kappa, for every P that is in S1A, a structure M is kappa saturated if for every A that is a subset of M with cardinality less than kappa, every one type over A is realized in M. Okay, and you can also show that this is equivalent to saying that for every n that is a natural number and every n type over A, it is realized in M. Okay, so what does this one mean? It means that these structures M is very rich. It is very rich. It can realize every type that we can have with the condition that you shouldn't have too many parameters that is allowed. Okay, and one thing that I would like to point out is this is a strict order. This is less than, strict less than, because if you're set A, if you have a structure M, and if your A has cardinality, let's say if it has cardinality kappa, which it is less than K. Keep my finger. Okay. M is kappa saturated if for every A that is M is kappa saturated if for every A that is a subset of M with cardinality less than kappa, this guy is realized in M, right? Let me point out something. If you look at M, and if you have a set A that is of cardinality equal to M, there is and if A is equal to M, then you can get that this guy cannot realize this guy. Why is that? Because you can look at the type that say something like here. So you can look at this sigma x, where sigma x is a set of x and it's not equal to A for every A that is in M. And you, if M is infinite, then you're gonna get that this sigma x is finally realized, right? And since you know that it is finally realized, it must be consistent. And if it's consistent, right, then it must be realized then it must contain in P for some P in S1A. So now you can have that It is contained in a complete consistent N type, but this P is not realized in M because you say that nothing in M can be a realization of this type. So that's why we need to have the condition on the cardinality of the parameters so we can get rid of something that is like this. But we can show that if you have kappa that is for any kappa that is infinite and larger than the size of your language, if you have M that is structures, you can always find an elementary extension N of M that is kappa plus saturated, and you can control the cardinality of N. So it's not too large. Okay, so how we can do that? Let me point out something. This guy is equal to this cardinality. It is equal to where does this come from? It is an upper bound of the number of S1. Okay, and A that is less than or equal to kappa. Okay, so this guy come from, it's gonna be an upper bound of this cardinality of the union of S1A, right? For every A that is of size less than kappa. So because we want to look at a structures, right, that realize every type in M with the set of parameters is not larger than the kappa, right? So what we're going to do is we get these upper bound from the worst case possible, right? We look at what is the largest possible size of these S1A, the union of S1A when the cardinality of A is less than kappa. Okay, and how do we construct these elementary extension? The idea is we will try to list all of the possible one that we can have. So let's see this. So here, what we're going to do is we're going to start from a set M, right? And we can look at the set of A, where A is a subset of M, and the cardinality of A is less than kappa. Okay, so here we can look at this guy. And what we can do next is we can enumerate.
Excuse me.
Mm-hmm.
Excuse me.
Uh-huh.
I think the cardinality of A is not less than, but less than or equal to kappa, because you are going to construct.
Oh yeah. Right.
Rate.
Thank you, kappa plus. Thank you. Mm-hmm. This is less than or equal to. Thank you. Mm-hmm. Let's kappa plus, just because we're going to construct kappa plus saturated. Okay, and what do we do here? Next is we're going to enumerate all the types, all types of one type in here, in here. So we gonna let this be P alpha, where alpha is less than, yeah, let's just put P alpha then. Okay, and what we can do to construct these elementary extension is we going to construct a tower of this M alpha. So we start from M0, M1, and so on. We construct this recursively. So we let M be the base, our base. And we gonna construct the next one by saying that I'm gonna look at an elementary extension of my previous guy. And I'm gonna make sure that it realizes P1. And we're going to repeat this process until you reach the when alpha is limit ordinal. What we can do here is we're going to take the union of M psi, where psi is less than alpha. And by using the properties on the elementary chain, we're going to get that this is the model of, this is an elementary extension of M. So in this case, you're gonna get an elementary extension here. And we keep repeating this process until we ran out of all these P alpha. So let lambda be equal to this cardinality, so I can have the index here. Okay. So now, now that we have this, but it's turned out that when you have these M, right? These M gonna when you complete this process, you're gonna have M prime, and M is an elementary extension of M. And what is the property that these M possess is M possess the property that for every A that is a subset of M with the cardinality of A is less than kappa, then you're going to have that M prime realizes every type in S1A, right? However, this is not the one that we want yet, because we want M, these guys to be M prime, not just M, right? We want these two to be the same. So we still have work to do. So in order to achieve that, we're going to less than or equal to, not less than. In order to get that, we're going to make use of the fact that kappa plus is a regular cardinal. Okay, so what do we do next? So now that we know that we have M, right? We can go to M prime here, right? So we're gonna construct a new tower Here we let M be the sky. We know that when we have these n 0, we can construct n1, which is come from our construction that we get before, and we can keep repeating these process. Okay, and now we're going to do this kappa plus time. So which means we're going to have a sequence in alpha where alpha is less than kappa plus. Okay, and why do we need to do that? The good thing about the sky is once we have this tower and we take our n to be the union of alpha less than kappa plus and alpha, then when you have a set A, for A that is a subset of the universe N, you're gonna get that this A must be contained in alpha for some alpha. Okay, well, why is that true? Because if you have A, you need this as well. When you have A that is cardinality less than or equal to kappa, since kappa plus is regular, so you cannot have an unbounded map from kappa to kappa plus. So you have cardinality of A is less than or equal to kappa. So yeah, you cannot have an unbounded if A it does not contain in alpha for any alpha, you're gonna have an unbounded map from A to kappa plus, which is gonna contradict the property, the regularity of kappa plus. So that's how we know that we can construct these n prime. Okay. So, but these also implies that when you have a structure M, you can construct an extension, elementary extension that is kappa saturated. Okay, so here you can see that when you have a kappa saturated structure, it is very rich. It can realize every one type if your set of parameters is less than the cardinality of parameter is less than kappa. Okay. And you also know that when you have a structures M, you can go to an elementary extension that is kappa saturated for kappa that is larger than the size of your language. Okay, and here there are several other ways that we can show how large, so see that kappa saturated structure is large, it's rich. So if you have M and MB structures and AB is a subset of M, let F be a function from A to N. We say that F is elementary if for every formula phi x, A that is in A to the N, and M is satisfy phi of A if and only if N satisfy phi of FA. Okay, here this is just elementary function because the domain of these structures is not a structure. the domain of this function is not a structure. Okay, and we say that M is kappa homogeneous if for every A that is a subset of M with cardinality less than kappa, and for any B that is in M, every elementary map from A to M can be extended to elementary map from A union set of B to M, or or you can say that if you have F here and you have B that is also add one more object to your function, and you know how to you can extend your function to that point, and it's elementary. Okay, so that's what kappa homogeneous mean, and we say that M is kappa universal if for every n that is logically equivalent to n, and if cardinality of n is less than kappa, then there exists an elementary embedding from n to m. Okay, so it's kind of say that if m is kappa universal, it means that for every n that is elementary equivalent to m, if it's not too large, you can embed it into m always.
Excuse
Okay.
me. I think it depends on the definition, but in my opinion, the definition of kappa universal should be the cardinality of n is less than or equal to kappa, right?
I usually use less than, and then yeah,
Because
I think when you
if you say countably universal, then in my opinion, it should be every countable model can be embedded into such a model.
Countable universal, that will mean, for me, that will mean unloved one universal then.
Okay, yes.
Yeah.
Yeah, it
Right.
depends on the definition. It's
Right.
right.
I think it's dependent on the definition. Okay. And here, if you have kappa is saturated, then you can show that it is kappa homogeneous and it's kappa plus universal. And why is that? If you have that kappa is saturated, right? M is kappa saturated. To show that it is kappa homogeneous, so you let A be a subset of M with the cardinality of A is less than or equal to kappa, and you have F be an elementary map from A to M, and you have B, which is an object in M. You may assume that B is not in A, because if B is in A, then it is obvious. So let's assume this. Okay, now what can we do here in order to find this? Since you have B is not, you can consider the cardinality of A union set of B. if A is the cardinality of A is less than kappa, then you're gonna get that the sky is less than kappa as well. And the idea on how we can construct the type and the extension of this is we're going to use kappa saturated to tell us like, oh, what can we send this B to? So how do we do that? We can consider the type of B over A. Okay, so this is a type of B over A, right? And you can consider this guy, and then you can look at this guy, FTP B over A, which is the set of phi x and then FA for when you have that phi xa is in TP B over A. So what does this notation mean? It's mean that you're gonna look at LA formulas here. And what you're going to do is you're gonna list all the formulas, all the constants, all the parameters that come from A. You put it in here and you look at all the formulas that of this form that is in the type of B over A. And then you're going to look at the sky right here. You map the sky, you map all the parameters from A to F of A. Okay, and now by mapping it this way, you can see that this guy is an N type over the image of A. Okay, and now when you consider the image of the cardinality of the image of A, this guy is less than kappa, right? So what you can do is you can pick a point C that is in M. Let me use D. A point D that is in M that realize TP, FTP, FTPBA. Okay, so you can pick, since M is kappa saturated, then you can pick a point D that realize FTPBA. And it's, you can easily, you can check that if you extend F by a map by this, you get, you map B to this D, then this extension is elementary. Okay, so that's the idea of how we can construct this. Okay, so that's the idea of how we can show that it is kappa homogeneous, and to show that it is kappa plus universal, what we can do is that, so we gonna let N be a structures that is elementary equivalent to M, and cardinality of the universe is less than kappa, equal to kappa. Okay, and now that for sake of simplicity, I'm gonna let lambda be equal to the cardinality of n. Okay, so how can we show that it is kappa plus universal? So what we're going to do first is we're going to enumerate n by this guy, a alpha for every alpha that is less than lambda. So we're going to enumerate this guy here. And what we're going to do next is we're going to have n right here, and we have m here, right? So what we're going to do is we're going to construct a map, elementary embedding from n to m, right? So this is what we want. We want to construct this f. So how can we get it? Here we know that object in here gonna contain a0, a1, a2, a3, and so on. So you have lots of object in here, and you want to know how to map it to this side. So what we're going to do is we're going to construct a sequence and a sequence of a function that map things from here to here. Okay, and by constructing this, what we want to have is we want that for every step that we construct, we want all of these map to be an elementary map. Okay, so that's what we have here. And how can we guarantee that we can do this? So first, what we can do is since we have that n and m are elementary equivalent, thn is equal to thm, right? So what we can have here is at the very basic step, we're going to have that the empty function is an elementary map. Okay. And now that we have this, what we can do next is, since this is, so next what we need to do is we need to determine like what should I map this guy to. Next, let's consider at a0. I need to determine what can I do with this a0. So what we can do is we can look at the type of a0. And since this is a type in S1n, right? So you're gonna get that this type of a0 is also in S1m empty. Now that we have that this guy is in S1m empty, since m is kappa saturated, then you're going to get that once this is saturated, then you're going to get that this guy is realized. Okay, so you can let that be 0 realized TP A0. So you're gonna get that, oh, you can map it to B0 here. And you can keep repeating these process and get B1, B2, B3 by keep adding collections of what we already have so far. So let's see, for example, you can consider the type of A1 with the set of A0 here. And you get map it to A0 and then B0 here, right? And then you say that B1 realize TP is A1, sorry, not A0, over the set of B0. And you keep repeating this process, right? And when alpha is limit ordinal, you're gonna take F alpha to be.
Excuse me. Your notation of type A1 over B0 seems to be a little bit strange because A1 and B0 are living in other models.
Oh yeah, right. Oh yeah, I shouldn't write it like that, right? Thank you. I should just do it like what I did in the previous one. Thank you. This is F1. A1, right. Thank you. I was A0 here, sorry. And right, so the next step gonna be something like you want to look at the type of A2, it's gonna be A0 and A1. And then you look at F2, type of A2, and then A0, A1. And then you let B2 realizes F2, TP, A2, A0, A1, and so on. And you're gonna let F alpha to be the union of psi less than alpha of F psi. Okay, and yeah, and by taking the union of all these F alpha for every alpha that is less than lambda, you're gonna get an elementary embedding from n to m, because you make sure that at every step it is an elementary map, and you know that right now you exhaust everything in the n, so you use everything in the domain here, so it must be a map from this to that. Okay, so that's how we show this. Okay, so the concept of kappa saturation is, it is a structure that is rich. It realizes every types that can be realized. The other direction is to talk about the omitting types. Oh, okay, there is a chat in Shala's book classification. He defined a universality by using less than or equal to C page 5. Okay, I will check that out. But what I usually use, I use less than. Mhm. I think it, let me, oh, yeah, I'll check that and I'll let you know. Okay, next, let's talk about the other direction then, the omitting types. Okay, let L be a countable language and let T be a complete consistent theory. Okay, here instead of consider, since we already know that if we have M and M that are elementary equivalent, then you're going to get that the type of M, the MD type, they are equal, right? So you know that these two types are equal. So what does this one mean? It will mean that you can think of the concept of type instead of thinking of it as depending on the structures. Actually, it depends on the theory, right? If they're both the same, the model of if M and M if M and N are model of the same theory, then you're going to have that the type over empty set of these two structure are the same anyway. So you can think of it as something about theory. Okay, and we can define pretty much an analog of all the definition that we have above in terms of the sky in state. And N type in T is the set of sigma X, the set sigma X of L formulas with 3 variables among X1 up to Xn. And we say that an N type is consistent if T union sigma X is consistent, and it is complete if for every L formulas phi is in sigma X or not phi is in sigma X. Here we can write SNT to be the set of all complete and consistent N types in T. Okay, and here let phi x be formulas. We say that phi x is complete in T if for every psi x, either for every x, phi x implies psi x, or for every x, phi x imply not psi x. Okay. So what does this one mean? It will mean that phi x for any formulas, it can imply like either psi or negation of it. Okay. And we say that sigma x is an N type in T if phi x isolates sigma x, right? And T union phi x is if it is consistent and its phi x is either implies psi x, no, and T proves that for every x, phi x implies psi x for every psi x that is in sigma x. Okay.
Excuse me. Are you always assuming T is complete?
Complete, yes. Here, complete
Right.
and consistent. And L
But
is
the omitting type theorem holds for any theory. It is not necessary to be T is not necessary to be complete, right?
sorry, if you mean in order for this definition to work or something?
Yeah, T is complete, all right, but the omitting type theorem holds for any theory.
hold for any theory.
T needs not to be complete. T is not
Omitting-
necessary to be complete for omitting type theorem.
But in that case, it will be let me think about it real quick. But in that case, it will be different here because it doesn't tell us something about the type of the models. If you have a model of T, you cannot say something about the S and T, right?
Yeah.
So what does
Omitting type theorem is a quite general theory. So general theorem. So it holds for all theory, for all consistent theory. But by assuming T to be complete, maybe some discussion will be easier. So you can assume T to be complete, but it is a general theorem.
Let me think about the.
Excuse me.
Okay. So let's.
I will.
So let me. So if. Oh, okay. Then now I will check that, and I will let you come back to this next time. Okay. Right. Okay. Okay. So let's, before we go to the next part, let me quickly give you examples of isolated type then. So just to give you some idea of what this one means. So if you have a structures and you have a constant symbol in your no, you have a theory T, right? And you have a complete theory isolate. You have a complete theory T, and you know that your language have a constant. See, then you can have that if you considered a model, let's say you have M be a model of these complete consistent theory T, then you can consider the type of C. You can consider one type of C in M, right? And now what do we have here? Then you can have that the statement X equal to C gonna isolate this type. Okay, so that's roughly an example of what we can do here. Okay, now let's me talk real quick about the omitting types theorem. So it say that for every k that is in N, and we have countably many sigma k, if sigma k is not isolated, then there is a countable model of M, countable model M of T such that no sigma K is realized in M. Okay. So so we can say that or we can say that when you have countably many non-isolated type, you can have a countable model M of T that does not realize any of these sigma K. Okay, so what okay, so what can we do to get that? In order to prove this, what we can do is we can construct something that is similar to our construction of completeness theorem, but we're going to use the fact that it is countable. So what we're going to do is we're trying to add more sentences to these structures. So what can we do in here is we first gonna enumerate all the sentences, all sentences. Oh, and we need to add constant, add constant symbol to here, and then we gonna enumerate all the all sentences, and next we gonna enumerate all tuples. Like nk nk tuples of constant symbols that we add. Okay, so we have all these finite tuples, right? And we enumerate all of them. And here, what we can do is we know that this must be countable at countably many constant symbols, enumerate all the sentence, enumerate all the tuples. And what we can do is we were trying to construct it by in turns. So we're gonna construct a sequence of sigma t, where t is a natural number, so that it satisfies the properties that if t hold for t that larger than s. So we're gonna trying to add more information to this sigma t. And the idea of how we can construct this is we're gonna divide it into 3 steps. At when t is equal to 3m plus 1, what we're going to do is we will decide whether want to make it complete, make it more complete by deciding whether to add the sentence. Let's say I have sigma m here. So we're going to decide whether to add sigma m or not sigma m, right? And for it is plus 2, we're going to make sure that it has the witness property properties. Okay, and for the divisible by 3 cases, what we're going to do is we're going to make sure that it when you consider the tuples of these constant symbol, it doesn't realize something, right? Any tuples, there must be some type that it does not realize. Okay, and I think I'm running out of time, so I might just say something like this. So just say so idea is we just say that we can add sigma m or not sigma m. The next step is once we add it, we can make sure that it has witness property. And the third part is to make sure that it doesn't realize something. And by completing this, we can get that we obtain the omitting type theorem. Okay, and as a result of omitting type theorem, we can get that actually isolated type are the one that is sorry, that is necessary here. That is necessary to be that materialize in every model of T, right? So here we have that if sigma is isolated in T, then sigma is realized in every model of T and is also realized in all countable model of T. Okay, the one implied two immediately from the definition of sigma is isolated. This guy is trivial. The one that needs omitting type theorem is this direction. So what we can do is we can look at the contraposition of this. So you're going to have sigma that is non-isolated. And then you, by omitting type theorem, you can have a model of sigma, a model of T, and sigma is not realized in M, and M is countable. Okay. Yeah, I think that's it for today.
Okay. Thank you, Athipat. Do we have any questions for our speaker? Or any comments? Extra comment? Yeah, Akito, do you want to just say that?
Yes, assuming T to be comfortable is all right, because by assuming such a thing, a proof can be a little bit easier. But to get a counterexample for uncountable theory, which does not hold, for which the omitting type theorem does not hold, is a little bit difficult for a complete theory. For an incomplete theory, there is a very simple example. But for a complete theory, we must work a little bit harder. Yeah, that's my comment.
Oh, okay. Thank you. Thank you.
Mhm.
Yeah, and I think I remember now that it is not about the completeness, right? But I just was thinking about this part, and it kind of mess up my memory or something like that, because I wanted to say something like if T is complete, then isolated mean it is realized in every model of T. So I think that's probably something that mess up my memory.
Yeah. Yeah, I think this is a very interesting topic, and I remember studying it like 12 to 13 years ago. This was like the most challenging part of an introductory model theory I was doing. Yeah,
Right.
but it's
Let me
important.
say a little bit more. I think I want to mention about what would probably would like to say.
Mhm.
I think you want to say something about why this one. There is something that I want to say that I forgot as well. I would say that the condition that it is countable is important. And you can look at this guy where you can have a language that consists of these two set of constant symbols, where C is countable, and D is uncountable.
Yes, that's a very famous example, but this theory is not complete.
Right. That's why I think that this is something that you want to mention. And what you can do is you can look at this theory of not theory, that you can look at you can look let me look at it. I forgot. Okay. And you can look at this theory T, where T say that A is not equal to B for every A and B that is in D, and A is not equal to B, and you can let sigma X to be the set of X that is not equal to C for every C that is in C. And you can look at complete extension of sigma X, and this one cannot be omitted, but it's not isolated. This type is not isolated, but it cannot be omitted, because you have, in every model you have in model of this must have uncountable objects, so it must realize in every model. Okay, so that's what I would like to.
Any other question for Athipat? Okay, if not, thank you, Athipat, and thanks for all of you who attend. So I'll see you guys again in about 25 hours time. And thanks, Athipat. I'll see you again.
Okay.